Hello everyone and welcome back. My name is Mr. Cobalt and in this video I'm going to be talking about rate laws. So we're continuing the series in Introduction to Kinetics. This video I'm going to focus on rate laws. So what exactly is a rate law? A rate law is basically an equation. It's a mathematical expression that mathematically, of course, shows the relationship between the rate of the reaction, the chemical reaction, and the concentration of its reactants. And it only takes in consideration the reactants. So here we have our general equation, our generic equation, where I have A plus B equals C plus D. A and B are the reactants, C and D are the products, and the coefficients are the small letters A and B, C, and D. Okay, so the rate law is going to give us an expression here that relates the rate of the overall reaction to the concentrations of the reactants, so A and B here. And so this relationship is also takes into consideration these exponents x and y. And I'll talk about x and y in a moment. But this is our expression here. And this k value, that's called the rate law constant. I'll talk about that in a little bit. But this is what our rate law looks like for a particular reaction. It's going to be the rate is equal to k multiplied by the concentration of A to some power x, and then multiplied by b raised to some power y. And again, I'll talk about what those powers are and how we get them. Okay, so let's talk about orders. So reaction orders, this is where we're going to talk about our exponents a little bit. So reaction orders are the exponents in the rate law, and they tell us a couple of things. So they tell us the order with respect to the concentration. So what that means is that how your concentration of A changes is going to affect the rate of the reaction in some way. Also, how your concentration in B changes is also going to affect the rate in some way, and that's where your x and y comes in. And just to make sure everyone knows, these square brackets around the A and B that represents concentration of. So the square brackets means concentration of. So square brackets around A is concentration of A. Square brackets around B is concentration of B. So I just want to make sure everyone understands the notation. All right, so the order is represented by this. So if this was a 1, if x was 1, that would be first order. If y was 2, that would be second order with respect to b. If this was a 3, it would be third order with respect to b. If this was 3 here, it'd be third order with respect to a concentration. So I'm talking about concentrations. So it's the order. Well, what does it mean, the order, right? What does that word mean here? So it's the mathematical effect that an individual reactant is, the concentration of that reactant is going to have on the overall rate of the reaction. So that is, how much does a change in the concentration affect the overall rate? That is what we mean by the order. Okay, so how do we talk about this? How do we talk about our orders? Like as I said, if whatever the x power is, that is the xth order with respect to a. So here x again, if x is 1, it would be first order with respect to a. If if it was a 2, if the x here was a 2, then the order of the rate order with respect to A would be second order. So we're focused on only A here. If it was a 2 for B, it would be the rate order would be second order with respect to Y, or with respect to B. Sorry. Uh, And then the reaction, the order of the reaction order itself is a combination of both of those. You add the orders together, and that is the overall order of the reaction rate, the overall order of the reaction rate. So if x was a 2 and y was a 2, then the overall order of the reaction rate would be fourth order because we add the 2 to the 2 and we get 4, right? If it was first order with respect to A, but second order with respect to Y, then you add those together and you get third order. So the overall order of the reaction rate would be third order. And so that's how you talk about these things. All right, so next I'm going to talk more about orders as well as this K value here. So I'll just bear with me in just 1 second. I'll be right back. Okay, let's now talk about K. What is K? Well, K is called the rate constant. And so what we're talking about is this K right here. So again, here's my generic equation. Here's the rate law, the generic expression of the rate law. And what K is a numerical expression that relates the rate, the reaction rate, and the concentration of reactants at a given temperature. So this means that different reactions are going to have different K values. This also means that since this is at a particular given temperature, the K constant is going to depend on the temperature. So different temperatures are going to give you a different rate constant. And so also how big the K is, or the rate constant, is going to determine how fast the reaction is going. So larger K values means that the reaction is going to proceed more quickly than smaller rate constant values. Okay, so that's a little bit of an introduction to what we mean by K here, what this represents. And now let's talk more about where the orders are coming from. Okay, so now we're going to talk about where do we get our rate orders from. So the first thing we need to realize is that our rate orders are always determined experimentally. We can't just look at our balanced equation and see what the orders of our reactions are going to be with respect to either reactants or the overall rate order of the reaction itself. So the exponents are not going to be the coefficients from the overall balanced equation. There's one instance where that's going to be. I'll talk about that in a moment. But the exponents are going to be coming from the rate determining step of the reaction. So if the reaction has multiple steps, we talked about before how one of those steps will be the rate determining step, which means that that particular step is what controls the rate of the overall reaction itself, right? So again, as an analogy, if you have a single lane highway and you have one slow vehicle and you got a bunch of other faster vehicles behind it, well, those faster vehicles are only going to go as fast as the slowest vehicle, assuming they can't get around or past that vehicle because of oncoming traffic, right? So you're only as fast as your slowest vehicle. And so everything, the speed of traffic is going to be determined by whatever that slowest vehicle is, right? So in the same way, your rate determining step determines how fast your overall reaction is going to be. And so that's where we get our orders from, is from the rate determining step. Now, there is one example, exception to that, and I'll talk about that in a moment, but here's an example of what I'm referring to. So here's our balanced equation for this reaction, and here's the coefficient for ClO2, and the coefficients for F2 and FClO2. And so here's the reaction rate expression, and you'll notice that the concentrations of both F2 and ClO2 are raised to the power of 1. So we don't usually write ones down. So there's ones there. And so if we look at our balanced equation, ClO2 has a 2 coefficient, but its exponent is 1, which means that this is first order with respect to ClO2 concentration, and it's first order with respect to F2 concentration. It's not second order. Okay, so this is an example of how the coefficients aren't necessarily going to be the orders or the exponents on your rate law expression. Now, this indicates then that there must be multiple steps to this reaction, and whatever the rate determining step is, that's going to determine these values for the exponents, the orders. Okay, now there is a situation where what if the reaction is a single step? It's not multiple steps, it's single steps. So if it is indeed a single step reaction, then of course that step is the only step in the reaction, and therefore that step is the rate determining step, and the coefficients for that rate determining step is going to be the exponents in your rate law expression. And so in this case, the balanced equation, the coefficients in the balanced equation for your reactants would be the coefficients in the rate law expression. All right, so what about the steps in determining order? How do we determine the order of your reaction with respect to a certain reactant? Well, let's go over that now. Okay, let's go over the steps that you would have to take to determine the rate order of a reaction. So let's get into this. So first step you want to do is write your skeleton rate law. So what is the skeleton rate law? That's basically what I had before. We use red. So your rate is going to be equal to some K value multiplied by the concentration of A raised to X power times concentration of B raised to some Y power, and so on for any other reactants that you might have in your balanced equation. So you start with that, and then now you're going to look at your experimental data chart. So remember, the rate laws are going to be coming from experimental data, and a lot of times they'll give you an experimental data table where you'll see the concentrations being changed and rates being measured, and they'll compare changes in concentration of each reactant to the rate of the reaction. So you're going to look at your table, and then you're going to find two trials in which one, the concentration of one substance is held constant and the concentration of another substance is being changed. Now, the one that's being changed is going to be the one that you're interested in. So, for example, if I want to find the order of the reaction with respect to A, then I want to see how the rate of the reaction is affected by changing A while keeping B constant. So I'm going to be looking for two trials in which the concentration of B is not changed, it's held the same, while they're changing the concentration of A. So I'm looking for those two concentrations in my table. If I was looking for B, right, I would find two trials in which A is held constant while B is changing. And so I would look at how the rate is affected by the change in B only. So I only want the change of another substance to be changed, right? The concentration to be changed. And I'm looking to see how that rate changes when I vary the concentration of only that one thing I'm looking at, right? So this is a step-by-step process. So then I figure out what the exponent on that concentration change that would result in the observed change in rate. So basically that would give me the order with respect to that reactant. So for example, let's say I pick two trials where B is held constant, the concentration of B is held constant, but A is being changed. And let's say I double the amount of the reaction. or the concentration, right? So if I double the concentration of A, I look at the rate. Now, if the rate does not change, that means that the concentration of A is not affecting the rate. So that would be 0, right? So that would be a 0 for my exponent, and anything raised to the power of 0 is 1. So basically, A would not be part of my overall rate law, right? So it would be dropped. So, but what happens if I double A, right? Let's say I double the concentration of A, and the rate of my reaction doubles. My reaction rate doubles when I double the concentration of A. Well, in that case, it's a one-to-one relationship. So here, that would be a 1. My X would be a 1, and so I'd have the concentration of my A raised to the 1 power. So that would be first order. Or let's say again, when I double the concentration of A, my rate quadruples. Well, what exponent would I need to get that sort of effect, to get the quadrupling effect of that rate? Now, so if I double, right? So let's say I say X. If I double X, my rate gets quadrupled, multiplied by 4. So the rate gets multiplied by 4. So I quadruple the rate when I double the amount of concentration, right? So let's write this as concentration. So I double the concentration of A, and I quadruple the rate. Well, if I multiply, or if I divide both sides by 2, then I get 4 over 2, which is 2. So I get a double. So it's a doubling of this. So my order here, my exponent, is going to be 2, right? So I guess another way you might think about it, maybe a better way to think about it, is if I double my concentration, right? The concentration, if I make it double, 2 times A, I double the concentration of A, and I get X, and I quadruple the rate, right? What would X have to be in order to quadruple that? So if I get 2 to the X power is equal to 4. Well, what is X going to be? Well, X would need to be 2, right? 2 to the power of 2 is equal to 4. So I could figure out that in order to quadruple the rate, when I double the concentration, my exponent would have to be 2. So maybe that's a better way to think about it. So that's precisely what you're trying to do. You're trying to figure out what exponent you would need to get the change in the rate that you observe from whatever change in your reactant you're getting, right? So you're going to have to figure that out. And then once you figure it out for one reactant, you do it for any other reactant in your skeletal rate law. And then you'll see what comes about, right? So that's pretty much it for the steps. That's it for this video. In my next video, I will go over some practice problems where I show you how to go through the steps to figure out your rate law and maybe even calculate the rate constant K. So if you enjoyed this video, if this video is helpful in any way, then please, by all means, like the video, share the video, hit that like button right there. Also, subscribe to my channel, hit that notification bell. Also, make sure you hit all when you hit the notification bell so that you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Let me know if you have any questions. I would love to hear from you. Thanks for joining me, and have a great day.